Okay, participants, good afternoon. Let us start the session. Others will be joining gradually. Our speaker for this particular session has already joined, so let us not wait for more time. Sir, Ravi sir, am I audible, sir?
Yeah, yeah.
Uh,
Yes.
we start now.
Yes, sure, sure.
Okay, participants, welcome back to this afternoon session. Uh, for this session, we have Dr. Y. Ravi Kumar. He is an associate professor in the mechanical engineering department at NIT Warangal. He obtained his BTech degree from JNTU, Masters from PSG College of Technology, Coimbatore, PhD in mechanical engineering from Osmania University, Hyderabad, and he has also postdoctoral experience in the domination of 3D printing at Milwaukee School of Engineering, USA. So he has supervised more than 30 MTech projects and produced 4 PhDs, and currently 4 PhD scholars are working under him. He has, to his credit, more than 70 research papers in reputed journals. He has filed one international as well as 2 Indian patents. Means one international and 2 Indian patents have already been published to his credit. He is instrumental in setting up a rapid prototyping laboratory at NIT Warangal. Um, and he also contributed in starting MTech program in additive manufacturing in collaboration with the Central Manufacturing Technology Institute, Bangalore, first time in India of its kind. He has established a world-class metal 3D printing facility at NIT Warangal under TechUp grant. He has conducted more than 15 training programs across India and trained around 900 participants in the domination of 3D printing. He has received Young Engineer of the Year in 2009 from Government of Andhra Pradesh and the Institute of Engineers India. He has executed sponsored projects worth of around 1.25 crore rupees in the area of 3D printing. So we are very much fortunate to have him as an external speaker. On behalf of Department of Production Engineering, as well as all the participants, I welcome you, sir, to this particular session, and I thank you for accepting the invitation within a very short span of time. Uh, so I welcome you, sir. Please start.
Yeah, a very good afternoon. First of all, let me thank you, Dr. Mahapatra, for giving me this opportunity to present here. So I can see one object printer right behind you. Okay,
Yes,
so
sir, that is
yeah,
applicable at our department.
okay. Yeah, the demonstration is over on that. Now
Today
you are
morning we had the demonstration, sir.
okay.
Demonstration of
Great.
3D printing.
Okay. Great. Yeah. Very good afternoon, one and all. So, is my screen is visible to you? Uh,
Yes, sir, it is perfectly visible.
yes. Thank you. I welcome all the participants. Very good afternoon, one and all present here. And the today's talk will be on the data file formats. So, my focus of the talk will be on the file format. That is, as we know that 3D printing requires a digital data as an input. The design should come in a typically it is a STL file. So my talk will be revolving around the STL file, that is predominantly on the file formats side. And apart from the STL file, so my presentation will also covers the the problems, challenges, advantages of STL file, and of course, how it is getting overcome these challenges or problems through a new file format recently proposed by ASTM F42 committee, that is additive manufacturing file format, and future direction of this data file formats. And let us start with the introduction to the 3D printing design. So why? Because 3D printing has to start with a digital design. So that is a mandatory to start anything that is getting fabricated. So then it should come in a digital format. Of course, that design. So now I'm going to give some design tools of this 3D printing technology. So, and then we'll focus on the particular file format called STL. So then let us start 3D printing introduction. So what is the 3D printing design is all about? So if we take a typical 3D printing system, so we need to start with the solid modeling or a CAD modeling, um, the which is you are intended to fabricate. It should say come with a digital file, and that is then converted. Data conversion should be done. Why we need to convert that data? Say I might have used software like say Katia, and somebody else may use Creo, or somebody else may use AutoCAD. But as we know that each CAD system will be having its own native file format like .prt or .dwg or .sldprt. So, but 3D printer cannot directly recognize .prt or .sldprt or DWG. So in that case, which we need to convert that data into a particular file format. Typically, it is an STL file. STL stands for stereolithography. Incidentally, that was um, invented by Charles Hull. Um, Incidentally, the inventor of the first 3D printing technology called SLA, that is a stereolithography operators, and that is in 1988. Um, but still now also the STL file format as a de facto standard in the 3D printing industry. We'll focus on that part. And anyway, the data should be converted. Of course, it should be a .stl file, and it should be transmitted where you have facility of data. It should be a .stl file, and it should be transmitted where you have facility of printing that CAD data. So then before printing that, which we need to generate the codes, or we need to prepare the build setup, which is further sent to the machine. So how do you do prepare that code, like G code, M code, typically in a CNC system? So here, before preparing that code, we need to check the CAD file, which is in STL file format. Why do you we check that? Why do we repair? Sometimes we need to repair. Sometimes we need to correct it. So why do you want to do that? Is say your STL file may have some errors that we'll discuss in length. Maybe for checking the healthiness of your STL file, you may use other softwares, or some tools should be used to check, and then getting automatically repaired those file problems. Once it is free from all that errors, um, probably it should give some process parameters should be set. One may be like orientation, fabrication orientation, and then layer thickness we need to specify. And then we need to specify if it is extrusion based system, what what will be the speed of the nozzle, and if it is a laser system, what could be the typical laser power that is getting used to melt your material, or what could be the typical speed, scanning speed of the laser. So like that, and what could be the typical layer thickness of your part that is getting fabricated. So once you set all that parameters, and probably the support structure, which right now you can see, there are some supports should be generated wherever you have some overhanging portion. So we need to do all that stuff, and once you have done all that thing, and then you send that code to the machine, that layer by layer, how exactly you have done virtually here in the computer, so that is getting replicated physically here onto the machine. So that is a typical, say, a code preparation and sending it to the machine in terms of layers. So and then one layer upon other layer, so it is getting printed, and rather than it is getting stick together, and finally you are going to get a three-dimensional physical model out of, you name that as a model, or you name that as a component, or if it is an assembly, or it may be a direct product, end usage product also. That depends on the type of technology, the material that you are using it, and sometimes uh, the part that has come out from the machine, that is the as built part, may not directly, it cannot be directly used. Then we need to go with some post processing methods. Then post processing methods will vary from, again, one technology to other technology. Say for example, if you talk about SLA system, so typical SLA system, it must, every part must undergo an UV curable oven, that is ultraviolet curable oven, to cure your liquid 100% as a solid. Then we need to use a post processing method called UV curing oven, and you may use some other post processing methods. If it is a powder system, we need to, say, evacuate the loose powder, and sometimes if it is a FDM system, or if it is a material jetting system, then we need to have supports, then we need to remove the supports, and then several post processing operations. That depends on the type of technology and the application of the part also. Why? Because sometimes your surface quality may not be good, means which that may not be acceptable directly for your application. Then you may use say, typically sometimes it may be um, a furnace treatment, or sometimes it may be a short pinning, or sometimes it may be hipping, that is a hot isostatic pressing. So then that depends, the requirement, the application demands, and then you may use various post processing methods to enhance the physical properties of the part that is printed through this 3D printing technology. So this is a typical workflow that will take place in any 3D printing technology. So then right now our talk will be focusing on the data formats, means while converting or while saving your CAD file, um, and that should be recognized by your 3D printer. In turn, the software that is interfaced with the machine, then it should capable of reading that design. So typically that should be in STL file format. So we will focus at this point of time on that file format. Say, how do you get design your product? So typically you may use a 3D model capture method otherwise called as reverse engineering approach, or 3D scanning, or 3D digitization systems. Um, Along with some softwares or the tools like Kinet Fusion or Autodesk Recap, or any other tool that will support your 3D digitizing systems, so which you can capture if it is already there, some physical product or some physical object is already there, you want to just capture it, you want to scan it to get a digital data. So that may be the one of the methods to get your design. Or you can go with a CAD modeling route, so you can do right from the scratch. You can use a blender softwares like blender or fusion 360 or rhinoceros or whatnot, like say creo, katia, or whatever the software that is you are familiar, or which you have that software with you. So then you can do a modeling right from the scratch. So that may be another way of getting your digitized data. Um, Either it can be through a model capture or through CAD modeling approach. We need to save that file as STL file. Basically, STL file is a mesh file. So that mesh should be repaired. Why we need to repair that we'll discuss. Maybe some errors, some problems, and we need to check the healthiness of your mesh that is in triangular mesh called STL file. And then you may use some softwares like Netfab or Mesh Mixer or Magix. You have plenty of tools to do this job. Some of them are maybe open source softwares. And once it has done checking the healthiness of the mesh and getting repaired, and then we need to slice that model by using some slicer softwares like Cura or Repeater or Simplify 3D or any other software that is supplied by the vendor along with the machine. So then you can do a slicing of the model by using that slicer software. So then these are the typical steps involved in a typical 3D printing design process, and then further making use of the tools to get it sliced and generating a code for the 3D printing machine. And you may use any softwares like for that matter, even you may use AutoCAD Inventor or Spaceflame or Siemens NX or SolidWorks or whatnot. Like you can make use of these tools. And if you're not comfortable, or you don't have these tools, or still you can have one more option, like you have some design libraries which you can visit, like something like Thingiverse is a one digital library or the repository where you can download these models, which is already existing millions of designs that will, if that will suit your requirement, even when you not do modeling, you can make use of those designs, but only for the personal use or education purpose, but not for the commercial usage. So then you can even make use of these design digital libraries to download your files. Maybe you may have other GrabCAD is another community-based repository or a design library, which even you can make subscription to that GrabCAD, and you can even make use of some of the designs that are already available existing in the library. So these are some of the tools or the where you can get it started your 3D printing journey. And then we'll talk about some of the design tools. I hope everybody may be familiar about these CAD design tools. Typically, you may use it for your routine CAD CAM CAE applications. Like you do start with modeling. Say you can have 3D modeling, like that can be a wireframe, or it can be a surface, or it can be a solid model, which you can make use of several softwares, maybe some freeform softwares or say artistic softwares or some multimedia kind of a stuff like Maya or 3D Studio Max. Blender is another open source software like which you can make use of these, or Tinkercad is another open source software. And of course, you may have these proprietary softwares, CAD/CAM, CAE softwares, or even you have an Onshape um, software, which is even it will run for an Android based platform also. Like you have a plenty of tools or softwares that are available to get it started your 3D printing designs. And as we know that 3D printing technology has some unique advantages. What are those unique advantages? So then probably you are very much familiar about the um, modeling methodologies like parametric modeling, one the CAD, CAM, CAE softwares may use this kind of parametric modeling designing, or in the recent times generative designs, where you can consolidate the number of parts into say either a single part. Say I have some 10 number of components in an assembly, even I can make it a single um, part without an assembly. So then you can make use of generative design concepts, or even you can make use of a topology optimization tools, like where you can make more lightweighting of the structures, or even you can get it inspired these designs through biology, or through a cell biology, or through lattice structure, or through a biological designs, or a nature inspired designs. So then you may have plenty of tools to support these kind of design philosophies, but um, design is not the goal, but design may be the starting point. But what could be the goal? Then how do you get manufactured, or how do you get fabricate these nature inspired designs? So then the answer will be 3D printing technology. So why? Because the design complexity is free of cost in 3D printing technology, rather than it is say 3 times or 4 times costly in case of a conventional manufacturing process like machining or um, casting. Why? Because once the design complexity is increased, and then the cost of the production is also increased. But you have an advantage here through 3D printing technology. Your complexity is free of cost. So with that, we can make use of this 3D printing technology to fabricate any complex structures. That is the beauty of this technology, right? And then you may have several topology optimization tools or the softwares like Altair, OptiStruct, and even several say softwares available to optimize topology optimization of the designs. So then we can link this topology optimized structures to the 3D printing. Why? Because it is getting easily fabricated through 3D printing. So of course, as we already discussed, like you have some model capture tools, like you have say 3D scanning devices, or 3D digitizers, or reverse engineering, whatever you name this process. Then we can get the physical objects, get it digitized. First, initially, it is in terms of point clouds, and further it is an STL file. Then it can be send it to a CAE or CAM or 3D printing applications, wherever it is applicable. Then you can make use of this digital data which is derived from a physical object. So then you may use several scanners, several sensors to capture your data, right? Maybe a physical touch probes or a laser beam probes or optical CCD cameras, or even in case of a medicine, you may have a CT scanners can also be used it here, getting digitized and convert it as an STL file, and that is needed for the 3D printing technology as input, the data. So then you may use 3D scanning softwares like Geomagics and Kinet Fusion Recap and several packages available to reconstruct your physical um, models, the physical conversion of physical models into digital models. So then you can reconstruct them by using these tools. And repositories, as we mentioned, like you can go to their website or the repository community, and then you can download maybe GrabCAD or Thingiverse and many um, places where you can have millions of um, STL files or the native formats like .prt or IGS or step file formats, which you can download, and further you can get it printed onto the 3D printing machines. And of course, medical is also another area where nowadays this technology is very much popular. Then we'll talk about the design aspects or the digital data, where again you can collect from a patient through a digital X-ray or a CT, that is a computer tomography, or a MRI, that is magnetic resonance imaging, in case of a bone information or in case of soft tissues. So then you can uh, either use a CT or MRI scans to get your patient data initially in a grayscale images, and further it is getting reconstructed by using medical image processing tools, and finally you can reconstruct those images into three-dimensional models, and that can be used for printing further by using 3D printing technology. And even it can be interfaced to a CAD, um, say, to design some implant, custom designed implants, or sometimes the surgeons wants to do a simulation of the surgery, or generating some 3D computer models, or orthopedician say design some implant, some bone, and you want to test it against the failure of that thing, like then you can make use of FEM, okay, connecting or interfacing with FEM or CFD, a kind of analysis to study the blood flow in case of cardiac, or in case of neurosurgeons can do that, or orthopedicians or oral maxillofacial surgeons can do some finite element analysis on the patient data. And further you can get it printed, these physical models, to make use for a surgical model or rehearsal the model, or designing an implant, or designing a surgical guide template, or some um, say some instruments, patient specific required instruments, surgical instruments. So then you can do a several stuff here that is based on the data which is captured from the patient um, specific data, and further they can do some design validation on that patient data. And you may use several tools for doing this medical image processing kind of stuff, maybe mimic software, and you may have 3D doctor simpleware and other tools. And of course the open source software under this domain is a 3D slicer, which you can perform a preliminary operations like converting your medical scanned images, saving them in a DICOM image and further converting them an STL file. So that is needed for 3D printer to print that model. So then you can make use of these tools to do that job. Then we'll focus on the STL file. So the STL file is nothing but say typically we are talking about some interchanging of this data, why you want to interchanging of this data. So even this can be a quite common in case of an office printer. So an office printer can print a document, can print JPG, can print PDF, can print PPT, but how it is getting um, recognized by the printer. So of course, it should be getting converted into a PostScript form, and the printer can understand that PostScript form, and then it is getting printed. And similar way, the PostScript in case of 3D printing is STL file. So STL stands for stereolithography. Then you should save this file during your modeling phase itself as a .stl file. So what is a .stl file typically? So even you take any design data, the design data must consist of geometric information, must consist of color, must consist of texture, it must consist of material information, and so on and so forth. But unfortunately, STL file doesn't support all this, but it support only the geometric information. And basically, STL file is a triangular mesh, which you can see. It is basically a mesh which consists of an element as a triangle. And why it is triangle? So triangle is the simplest form of the polyhedra. So the polyhedra starts with triangle, um, and the planar triangles. Basically, these are the planar triangles, and which it is. You are going to approximate this, or you are going to tessellate the entire outer periphery of the model with the triangles. But STL file doesn't support color, doesn't support texture, doesn't support material, and etc. But your 3D printers can print in different colors, different materials. Then how do you um, get it recognized by the 3D printer? So though you're saying that STL file doesn't support this, so of course you may have other file formats that is getting converted into other file formats, maybe .obj or .mtl. So those are best fit for the color representation or high printing precision or for free-form curves. Why? Because these OBJ files are not approximated files, but these are free-form curves. The design that you have used some NURBS or a B-spline based model, but it retains as the same free form, unlike triangles in case of STL. And you may have other file formats in the recent times like ASTM, F42, T. They have developed a new file format .amf, that is additive manufacturing file. And parallelly, Microsoft is also developed .3mf file format. So definitely these file formats which consists of more information than STL file, but still STL file is maintaining as a de facto standard in the 3D printing industry. Yeah, and then we'll see the file structure or the STL representation. The typical STL file consists of triangular, planar triangles. And if you take a cuboid consists of 6 faces. On each face, you have two triangles. totally 12 triangles if you take a typical cuboid. But if you change the model from cuboid to the sphere, and you may have different set of triangles here, different number of triangles. It may be more in this case. Why? Because you have circular or a kind of a form here. It's not a flat surface. It is a circular. Then you may have more number of triangles that is getting represented. And similarly, if you may have other model, different geometry, different shapes, and you may have a different number of triangles. And if you try to save this STL file into an ASCII format, you can have two options. Either you can save it as an ASCII or you can save it as in a binary. But if you save it in ASCII format, so you can have this triangle. That information is basically, it is in 3 dimension, and you have the x, y, z coordinates of each vertex. You have 3 vertices, and the x, y, z coordinate of all 3 vertices. And apart from the triangle vertices, you have a one normal, so which is perpendicular to this surface, and that is an vector. The coordinates of the vector is given here. Like that is a typical one triangle, and each triangle must have one normal, and that normal vector coordinates and followed by the triangle coordinates. Then similarly, I may have other triangles, and all the triangle information will be saved in this ASCII format. And if it is a binary format, of course, it is a machine readable format. And it should follow two rules. One is the right hand rule, another one is the vertex to vertex rule. What is the right hand rule is it will distinguish whether a particular triangle is belongs to an interior surface or exterior surface. So if you follow the clockwise convention, so then that can be identified that triangle belongs to an interior surface. And if it is an anti-clockwise convention, so then that triangle contributes to the external or exterior surface. And it should follow the another rule called vertex to vertex rule. It will say that the adjacent triangles must have a common edge or a common side of the triangle. Then it must satisfy the vertex to vertex rule. Your STL file must satisfy. You have another triangle, adjacent triangle, it must have a common say triangle. It must be shared commonly. The adjacent triangle should be shared. And then talk about the advantages. You may have several advantages. Then the advantages are like easy conversion. Like as we know that it is basically a planar triangle element. So it is a mesh form, and the mesh element will be a triangle, and that too it is a planar triangle. It's very simple to represent rather than any other complex shape or complex mm, form. But it is very easy conversion once you have STL file, and wide range of inputs, like basically wide adoption of this file format by all the CAD CAM CAE vendors. So typically how it will work in STL file representation. So you may have a tessellation algorithm built in your software. So that will be taken care, the conversion or the representation will be taken care by this algorithm. So this algorithm is so popular or widely used, almost all the packages, the people are adopted this. It's a wide range of inputs. That's the reason. And then it may be very simple. If STL file you're using it for slicing the data, means your slicing algorithm. Basically, what is the next step? We need to slice this STL file into layers. So then if it is an STL file, so means every time you are trying to get an intersection point of your cutting plane with the triangle edge. So the mathematics involved in this is very simple, rather than using a complex forms or a complex curves. But it is very easy for a slicing algorithm to tackle um, a triangle mesh that is an STL file. And you have another advantage, the ability to split the models. So why I need to split the model? So my printer build volume is say 100 by 100 by 100, but I have a model of size 200 by 200 by 200 So then I need only 1:1 model. Then I need to split the STL file into two halves or maybe three parts, and then I can make three builds, and I can say join, or I can glue it, something like that. So then, which we need to even oftenly a splitting of the models is taking place. But if it is STL file, the splitting will be very easy. And though you may have these advantages, and definitely you have several problems also. So the problems, we can divide them into three broad groups. The first one may be the representation related problem. That is basically you are approximating your model, not exactly, you're not taking the um, the design. Why? Because you're doing an approximation, rather than say the curve is not recognized as a curve at the moment you saved as a STL file. So you are doing an approximation that you cannot do anything. But definitely you have that error here, the approximation error. And then you have some problems which are intrinsic to the STL file formats, like file size, truncation error, incompleteness, inconsistency, inconsistent normals, incorrect normals. We'll discuss on this the upcoming slides. And the some of the problems may be related to your tessellation algorithms or your data conversion algorithms, which are embedded in your software. So maybe some gaps or some internal walls or some degeneracy in terms of geometry or in terms of topology, or some incorrect intersections of these triangles. So these are some of the problems that we'll discuss one by one. So as I already said, basically, say you have designed something in your CAD package, that is surface uh, some surface patch which you have modeled it, for example here. This may be a .prt file, but at the moment you saved your .prt into a .stl file, so then your surface is now approximated, your curve is now approximated with the triangular edges. So means you are losing some data. Basically, you're approximating it. You're not carrying 100% the data in terms of this surface model, but you are approximating it. So, and then you may have the problems like intrinsic, like the file size is too big. Why? Because you have a redundancy in the file. Why you have a redundancy? That is syntax and semantics of the STL file. Means it must satisfy vertex to vertex rule. Say, then obviously you may have a redundant triangle information, or redundant sides, the triangular sides information. So that may be a more bulky in size. And one more problem may be a truncation error. Like say, you as a designer, you have supplied your say dimensions of say double precision real number while um, designing it. But at the moment you saved your model as a .stl file, so your double precision real number may be truncated to a single precision real number, so where you have the truncation error. And your STL file is not a complete representation. What do you mean by that? So though it have a geometric information, but it is lagging topology information, that is connectivity or associativity. That information is lagging. So the STL file doesn't support a topology information. So, but it supports only the geometric information. So that is the incompleteness, as you know that. And because of this topology is lagging, so your slicing algorithm has to do an extra uh, duty or extra job. It should first sort your all your coordinates, and then only the slicing will be started. But anyway, you have incompleteness because it doesn't support topology information. And then you may have inconsistency in, say, wherever you have appending of the two STL files, you have a lot of inconsistent tolerance values. So then that may be another issue. And inconsistent normals, say your normal should be always, it should projecting outside of the boundary, but it should not project inside to the boundary. Then if at all, if some normals, it is getting flipped, so the flipping should be done. And some incorrect normals, say you can even reverse calculate the normal coordinates from the vertices, right? So you can do that one. But if you compare the coordinates of the normals that is generated by your tessellation algorithms, and if you calculate a reverse calculation mathematically, if you do, and there will be a deviation from your coordinates of your normals, so then that may be because of the conversion algorithm. But anyway, you have some deviation will be coming here. And of course your data conversion algorithms may prune some kind of gaps or missing of the triangles, or the gaps will form, especially wherever you have one surface and you have other surface, and at the mating of these two surfaces, like say I have one triangle, say this triangle might have missed it. So once you have some missed triangle, and if you are trying to slice this, say imagine that I have to start my slicing, cutting this plane, say Z0, and then Z0 plus my layer thickness. So this is my position of my say slicing plane. So like that, I can get the intersection point of my slicing plane with the triangle edge. So then I can get my intersection point. Say for example, I have started somewhere here. This is 1, 2, 3, 4, 5, 6, 7, 7 and 1. Again, it must coincide. Why? Because then only it will ensure that you have a closed boundary. But unfortunately, you have a triangle got missed and it has formed some gap. Now it has become a puncture, or now it has become it's not a watertight model. It has become some defect here. Then you try to say get it fabricate that cross section or that layer you are trying to say fill the contour. Your algorithm is trying to do that. Your code is trying to do that, or your laser, if it is a laser driven system, the laser has to trace that, but you don't have a clear cut boundary that where it should fill your tool path inside that. But you don't have such kind of a thing because you have one triangle got missed here, right? So then in this way, like you may have this kind of problems while processing your data. And internal walls maybe some kind of internal walls due to the improper joining of the objects may takes place, or some degenerate facets. Like it can be say you may have say vertices but it may not be contributing towards area of the triangle. Why? Because say you may have the vertices maybe three or a two which are located at the same point, but it's not contributing to any area of the triangle. So in that case, which it may have some degeneracy, that is a topology degeneracy. Or if you take other situation where even though you have three vertices with the different coordinates, but all are in a collinear fashion. But again, it is not contributing to any area of the triangle. So then it may become some error, that is geometric degeneracy. So then it is another problem that you can come across by using these STL files. And then you may have incorrect intersection or some overlapping of the triangles. It is not allowed. Why? Because as per the vertex to vertex rule, or even none of the triangles getting intersected, or it should not overlap one on another. Like it may be an extra triangle or it may be misplaced. We don't know if at all if it is there, and we need to correct it. We need to place it at a right place, or if it is additional triangle, we need to remove this. So then that's what way where your incorrect intersection or some triangles maybe lead to some errors. And then if at all if you have a valid model, so when can you say it's a valid model? Like this, it should have you have a three-dimensional model, and then once you slice it, and now you have exactly 2.5D slices. Why? Because you have a uniform thickness across all the layers. So then you have the 2.5D layers, and then it is getting finally 1D scanning lines by using a laser or extrusion head. It is getting deposited. So if it is a valid solid, and then you will get a clear-cut boundary, a closed boundary, and then you don't have a confusion to your hardware or to your controller to getting done this, right? So if you have some gap, some missed triangle, as we are discussing previously also, and you're trying to slice that invalid model or error, there is some gap or something got missed here, some triangle got missed here, and trying to get it printed onto the machine, and then finally you maybe end up with some um, build failure sometimes, or it may not give you the correct component or some error component you maybe finally end up with, right? So then we need to have a valid solid, and you should get a valid or a right or error free product. And then you may have challenges regarding the STL files, like maybe duplicate information or leaks or inconsistency, which we have been talking about. And it does not scale well whenever you are using with the high resolution data, or and even the lattice structures which you have in your model, then it may not give you a better result once you are working with STL files. And even it doesn't support any color information, right? Because additive manufacturing, 3D printing machines can print in different colors and different material and orientation, but it's not supporting this kind of attributes. And then what is the solution for this? And then ASTM, as we know that that is American standard for testing and materials. That is, and ISO also, as we know that this technology started in late 80s with the name called rapid prototyping. But ASTM has formed a committee called F42, and they are working out to develop or publish the standards for 3D printing or additive manufacturing parts. They have formed in after say it is almost like 2006 2007, but and after that ISO has formed, but still we need to evolve several standards, then only one can understand whether you made a bad part or a correct part. Once you have some comparison in terms of standards, right? So, of course, that's what ASTM has came into picture, and ISO along with the ISO, and they have developed some standards for this file format, that is additive manufacturing file format. So what is an additive manufacturing file format? It is an XML based script. Um, it is a format and it's a meta format, and it's basically a text based data, and it is easy to read and easy to write and easy to parse, and you can easily edit this XML script. That is basically AMF is an XML script, and you can easily edit, and it can be extensible easily, and it can be highly compressed form. You can do that. Say, what are the general concepts? Basically, your AMF file is not a mesh file. Previously, STL file is a mesh representation, but it is an volumetric representation, and you have even a material assignment, or also it will support materials also, and it will even support the colors, and it will support the texture mapping, and even it will support the grading of the material, like the functionally graded materials nowadays is very popular. Why? Because you may be expecting several properties in a single product at the several regions of your product, right? So then you have huge potential to work on such kind of materials, and then how you are getting printed those kind of functionally graded materials. And of course, your AMF file will also support the grading of the materials, and it will also support the lattice and mesostructures, and even it can be consists of some repeating instancing, packing and orientation. Also, it will support. Otherwise, STL file cannot support these characteristics. And then it will also address the duplication of the vortices, and it will also address any leakages of the mesh, or your basically your file consists of some leakages. So then it will also address, and then it may have some duplication. It will also easily identified, and that can be removed from this, and even it can be compressed at very high rates. Say I may have a typical file which is saved, and one time I have saved as an ASCII STL file format. Typically it may be consuming around, say, 780 790 KB, and the same file, if I save it as in a binary format, so it may be consuming only around 200 KB. But if you could able to save that file in a .amf file format, and it may be typically in between these two. But if I try to compress these three formats, and which you can see ASCII file may be compressed around 100 KB, and binary may be compressed around 50 KB, and whereas my AMF file will be compressed around 25 or 30 KB. So it is of more compressive in nature, this AMF file formats. And then how do you address your geometric accuracy problems? Like previously we were discussing about the STL file, which is of planar triangles, and which you will be obviously losing your accuracy if you have some curvature like this, but that curvature cannot be say what you call replaced with a triangle, the edge of a triangle, right? So always there is a deviation or there is an error. But how do you get addressed such kind of situation? Here is they have introduced a curved triangle rather than a planar triangle. So with that curved triangle or a curved patch, which you can even you are not going to lose any data. You are not going to get any error, geometric error, because this is your triangle is in a curved in nature. And even this will address your curved surfaces, and even it will support all three. Means like it will, wherever you have flat surfaces, and it is not correct to use a curved triangle if you are working with the flat surfaces. For the flat surfaces, you have planar triangles are very much sufficient, or it's the right way to represent. So means this will adapt the depending on the geometry of your model. So then it may even adopt a planar patches if you are working with the flat surfaces, and if you're working with the curved surfaces, so it will automatically adopt a curved triangles. And if you're working with some curved edges, then even you may have a curve, the what you call your tangent vectors can also be introduced here, and then your curved edges can also be easily tackled here. So everything can be done here without losing the accuracy of your model. And even it can be done recursive subdivision in the 4 power n planar triangles. Like you can refine your mesh in a more accurate way. And then if you try to estimate an error, if you take a typical sphere, unit sphere, and you save one time as an STL file, and you try to quantify the error, the cumulative error of the sphere, and then STL may give more error than AMF of a single fold, double fold, and triple fold, and so on and so forth, and which almost it is having a negligible error. So in that way, your AMF file is better, will tackle with the geometric inaccuracies. And multiple materials, like you have a provision that here you can um, represent what you call at say I have one region, one material, and other region, other material. Why? Because my 3D printers, um, some of the 3D printers can print in multiple materials. So in that case, my CAD file must also be represented particular region with one material and other region maybe other material. So I can describe or I can assign my materials here with multiple material assignment is also possible with the CMF file structures. And not only multiple materials, so if you want to do some grading of, so varying the composition, you have some Li, A, Li, B, and then I want to vary the composition and I want to represent it in my AMF file format. So it can easily done with this kind of AMF file format, representing the grading, functionally grading materials. And even it will support the microstructural representation. So I have some microstructures in my texture mapping in my model. So then that can be easily done here in this EMF file format. And then what is the current status of this EMF file format? Actually, the first version they have released in 2012. So now the test, they are doing a test for adoption. And in the recent times, even they have introduced the second version of this EMF file format also. Then what are the advantages of these standards? As we know that your standards will give you the industry to the next level. Means, say for example, you have some aerospace application of this typical a jet engine. So you're trying to make some jet engine parts, but who is going to give a certification or qualification of that jet engine parts? That can be flown into air means some kind of authority. The say FAA, that is Federation Aviation Authority, or some regulatory or authorities which they can issue some certification or giving some qualification of these parts. But on what basis they are going to issue a certificate, or on what basis they are going to um, give the qualification of these parts that can be um, fly in the air, then you must have some standards, and saying that, so by testing these things against that standards, that is the idea of the standards, right? Say you may have some kind of benchmarks or some kind of um, what you call, based on that you can test it, you can quoting that I have tested as for ASTM so on so, or ASM or ISO so on so standards. So then that's what it is happening even still. It is under development. This is one among ASTM F2915. So and this is about the file formats. The similar case for the feedstocks or the raw material standards also recently ASTM has developed, and for the um, say applications or post processing methods, or say the ASTM is in the recent times they are working out with various aspects of to develop the standards of these 3D printed parts. So then what are the future plans that in the next revision of this AMF file format, they are looking at the ISO and ASTM together. So they are they are going to focus on the tolerancing information. So far, it is not included the tolerancing information. Say, for example, you take a step file. So you know the difference between an IGS and a step file format. IGS is basically a design attribute representation of the data, but whereas a step is an complete product data information, which even it will support the manufacturing attributes, or like the tolerances, the manufacturing tolerances. So even the same way which they are trying to incorporate the tolerances information in the AMF, and the surface and the depth textures and data encryption or copyrights information, external references and sub-assemblies also they want to extend this thing, and the process controls. This is another stuff where the maturity of this technology, it should be further taken into the next level. How do you get a process control of these 3D printing technology, and of course in turn can it be represented in a file format like AMF, and even it can be a non-volumetric support structures also they are trying to incorporate in the upcoming versions of AMF. So and non-mesh geometry also, like voxel based representation or a feature representation, they are working on that. But the idea of these future formats of AMF from these organizations, to give a complete information about this product of a particular thing which it is getting 3D printed. And so far, we have discussed STL and AMF file formats. These are the two file formats. Typically, these are in a three-dimensional, or either in the form of a mesh or in the form of a volumetric uh, representation. But even after generating these codes, like your G code, M code in case of CNC, like you have a contour data that is basically a layered data format. So that layered data format, as of now, it is not standardized, and then various proprietary formats developed by Stratasys or US or um, SLM or 3D systems. You have several formats, but as of now, the contour data is, I'm talking about the build setup or the code that is sending to the machine. So you have the CAD file in STL file format and getting sliced and getting generating supports and getting codes. The code format is in this various several formats like stereolithography contour or stereolithography interface or common layer interface, rapid prototyping interface or a leaf. But still there is a need to standardize this format also here. And you may have other file translators. Normally you may come across IGS as we discussed, and maybe for printing scenario HPGL or medical scenario or for step you may be familiar, that is for the entire product model data. So what we have done the last 1 hour 15 minutes, like we have started with the importance of the design and 3D printing, of course a digital design, how it is important to proceed with your 3D printing um, application. And then we have discussed some of the design tools and the softwares in terms of CAD tools or in terms of model capture tools or in terms of a repository or digital libraries or communities which it will support, and then medical image data processing and the tools. And of course, we have thoroughly studied the STL file syntax and semantics and the file structure and the advantages of the STL file and the problems in STL file formats and the challenges of the STL file formats and how those challenges are addressed in a newly proposed ASTM or ISO file format, that is AMF file format, and the future plans of the AMF file format and some future 3D printing data file formats, maybe in terms of your contour data, that is the build setup data. Can it be standardized? But that may be maybe tough job, or maybe right now it may not be possible now, maybe in the due course, maybe the next down the lane 10 years or so, maybe you can expect some standardization of these data. Yeah, and before closing this session, just I want to give you some of the facilities which we have at NIT Warangal. We have a DMP Flex metal 3D printer. It's a powder bed based metal printer from 3D Systems USA. And we have a couple of Stratasysmic FDM based systems like Dimension and the Mojo printer. And even we have a desktop printers like Ultimaker and a couple of DIY kinds of printers, and AnyScan and SenseScan for scanning purpose. And we have a muffle furnace for post processing of this metal 3D printed parts to improve the mechanical and microstructural properties. We use muffle furnace to do that, and short pinning machine again for post processing of this parts. And then we have this softwares, then that is for medical image processing. So this is the software from Materialize Belgium, that is Mimic software. And we have Magic software that is for say doing some STL correction, some whatever we discussed, some problems of STL, so that can be corrected through this Magic software. And then Thematic software for say designing the implants for again a medical application. And then Catalyst, and this is a Stratasys software which will support for the status make of machines. And 3D Expert is the software for interfacing this metal 3D printer to do simulation kind of stuff and to do um, preparing the build setup for this machine, that is 3D Expert. Yeah, these are some of the softwares and the machines which we have at NIT Warangal. And when we have the YouTube channel also, then I will be pasting this link in the chat box. If somebody is interested, you can visit the YouTube channel and subscribe also. So I hope I have done from my side. And if you're having specific questions, and I am uh, happy to answer those questions. It is over to you, um, Dr. Mahapatro.
Okay, participants, if you have any specific queries, you can go ahead, unmute yourself and ask, or else you can type in the chat box.
Namaste, this is Kalicharan.
Yeah, Kali. Yeah.
Sir, how are you, sir? Sir,
I'm fine, thank
actually,
you. Yeah.
yes, sir. I need one suggestion here. How we will go with this one with the parametrical optimization? Can we put it here, sir? If we will put it, then what will be the input parameter and what will be the output parameter?
Um, okay, so means you want to do some optimization
Yes, sir.
kind of stuff. Okay, so means like you want to do it in you can do it in two ways, right? Like say if you're having a facility, so you can go for an experimental setup. Say if you have some machine, like if it is FDM based machine which you have at your facility, then you can try with parameters like layer thickness and the nozzle speed if it is FDM based system which you have at your place. And you can vary the say the scanning patterns styles, like you can even try with a contour kind of filling or a raster kind of a filling. And how these input parameters are varying onto the, say for example, the output parameter like strength. Say if you make some samples with contour filling of these tool paths, or you make some samples of zigzag or a raster kind of tool path, and then you can measure the strength mechanical properties of those samples. That is the output parameter. And similarly you can try for the dimensional accuracy. Then you have the CAD model, and then you have designed you know the dimensions of that particular feature, and then you make samples, and then again you test the physical samples. And then how do you get, say, optimum set of parameters? You can use some Taguchi experimental setup. By taking these input parameters, you have this output parameters, output response as either a geometric, say, or form errors, like you have some circular or cylindrical objects. So you can try with that. That is a experimental route, or you can do some mathematical modeling
Model.
kind of, yeah, model. You can develop a mathematical model
Sir, is there
simulated.
any surface that is surface finishing or smoothness or like this parameter? Anything we are getting, sir? As an
Yes, 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 yes. You are, yeah, the surface roughness, say, for example, you have RA value, and you have some literature available. Some others already developed some mathematical relation between your surface roughness, RA value that you fabricated through your 3D printed parts. Say, then you have the literature support for this in terms of these input parameters. And again, it will vary from one technology to other technology, and definitely you can find very good literature, especially for the FDM based technologies. But even powder bed systems, metal printers also, even you can
okay. Sir,
try.
nozzle, is there any effect of the nozzle temperature here, sir, with the material or the when you the layer layer by layer just the deposition of the material? Okay,
Yeah,
sir.
yeah.
During that one, is there any effect of nozzle temperature here?
Yes, definitely. Why? Because your nozzle temperature is one of the major parameters that we need to consider for, say, why? Because say you take ABS or you take PLA. Typically, these are the two materials normally you use for your FDM based systems. So definitely,
Sir.
um, it will have an effect on say shrinkage, or it will have an effect on your strength.
Sir.
Yeah, it will be having an effect on all these parameters. Then which we need to vary the temperature of your nozzle head. Like typically, you may set for the melting point temperature of the material. Say if you are using ABS, so it may be around say 230 or
Sir.
220 to 230 degrees C, and if it is a PLA, it may be less than that, maybe 180, 190 or so. So then definitely plus or minus to that melting point temperature. So then
Sir.
you can, it will be having a lot of impact on your
Yes.
shrinkage, that is mechanical properties and the dimensional accuracies. And yeah, then you
Okay.
can
Okay, sir.
initially, yeah, you can try with some experimentation and then mathematical, developing a mathematical model. You have a literature support also for this.
Yes, sir.
You
Yes,
can
sir.
refer
Yes,
some
sir.
papers. Yeah.
Okay. Okay, sir. Thank you.
Okay, Kali. Hello.
Yes, hello. Sandeep Kumar, do you have anything to ask? Sandeep? Okay, any other specific query? Okay, sir. So I don't think uh,
Uh,
this 3D printing will
excuse me,
be
sir.
applicable except some medical equipment.
Meaning will applicable? No, I'm not getting what he's trying to ask. Equipments. No, 3D printing can be applicable to various fields. One among maybe the medical um, field, and that too in the medical application. One among maybe the equipment. Maybe it can be an implant or it can be a device. um, it can be an equipment, so it can be anything that is that may be based on the patient specific requirement. Maybe you are trying to develop some implant or a prosthetic, so that is specific to that person or specific to that patient. um, that is an device, that is a thing, or even it can be an equipment for that matter. So that why? Because um, this technology will give you a customized solution or personalized solution to specific to that particular person. Why it is means each person or each human being is unique in their um, anatomy, in their geometry. Then typical scenario, they may use some standard sized implants or standard sized devices or equipment, but it may not fit right to a particular patient. But if you are looking for some patient specific, customized or personalized device, and definitely this technology will help you in that case. So none other than this technology will give you the solution for this kind of situation. So that may be the reason why this technology is so inclined towards medical applications. So it need not be the medical; it can be applicable to any other fields also. And if you come to the medical, and these are the probable um, say, yeah, the areas of applications which you can talk about. Yeah, food material. Can 3D printing be used in food material, and how can we use through which process? Yeah, yeah. Okay, yeah. Food material, food grade materials. Also now you have uh, great potential in the current times. Like you can even try with FDM based systems also there for food printing. Um, FDM may be the more appropriate process to make use of food printing. Um, but we need to follow some regulatory norms, maybe FDA or any other regulatory bodies which they can give a certification of these materials. Then now slowly it is coming up, but once it pass these regulatory bodies can give the approvals, then it can be further more popularized application of 3D printing. It's going to be the food printing. Yes. Yeah, you can have food grade materials nowadays. Yeah. Yeah, of course, the strength of the parts that is getting 3D printed. Um, yeah, this is a somewhat tricky question, and the why, because sometimes it may be better than, for your surprise, like um, some literature support also there for the statement. Sometimes it may be better than the wrought properties or the casted. Definitely, it is on par with the casted parts properties. And of course, it may be on par with wrought also, but definitely it is on par with casted properties, which you can quote it in that way. So, but sometimes it may be better also. But not all the process I can say, but some specific 3D printing processes can do that also. But after post processing, I'm talking about. I am not saying as built, but after doing post processing, definitely it is on par, or it may be better sometimes, but not all the times, but better sometimes. Yes.
Okay, I don't think there is any more query from their side. In addition to that, sir, today only we had a session where we learnt about the 3D printing of homes, that is concrete,
Okay.
3D printing concrete.
Mm-hmm.
As you have rightly mentioned, there are different aspects, different applications.
Yeah, contour crafting can be used for your this construction
Yes,
wasting,
sir.
construction waste. Yeah, there is a huge potential for the construction industry also. The application 3D printing in a construction is also coming in a big way in the recent times. So it is still getting just to take some maturity levels, and then definitely that is another sector. It is growing food printing as well as the construction industry, or um, yeah, that is a huge potential to tap. Why? Because you have shortage of manpower, especially it may consume several years together to build the houses or construction of the structures, but definitely it will give a promising application in that case. Yeah.
Yes, yes. So, I think we should conclude here.
Yep.
We'll be having sir with us tomorrow in the morning session as well. So we'll be having discussion
Yes.
tomorrow as well. So, sir, for this particular session, let me thank you for such a valuable session.
Thank you.
I can read out one of the feedback provided by Kavita S. That is, this is a highly informative session. Really, it was a very much informative session, very clear, at right pace, strong knowledge from basic to advanced. So we all thank you, sir, for particular session, and we look forward to see you tomorrow in the morning.
Yeah, thank you. Thank you, Dr. Mahaputra. Yeah.
Thank you, sir. Thank you.
Thank you. Thank you. Bye.
Participants, you can sign out now. We'll meet again tomorrow at 10 o'clock. So thank you, all of us, for your patient hearing. See you tomorrow. Thank you.
Okay, bye.